The phenomenon that all objects of mass feel pulled toward one another is called gravity. In the diagram below, gravitational force vectors represent the magnitudes and directions of the gravitational forces that would be exerted on a few objects at different locations around a sphere of mass, such as the Earth. Each object of mass feels a gravitational pull inward, no matter where the mass is located in space. These objects are said to be in the gravitational field of the larger sphere. To represent the idea of a gravitational field qualitatively, we can draw vectors showing the direction and the strength of the force that would be applied to a mass if one were present in the field. 3 examples of these drawings are below. Assume the spheres are infinitely far apart from each other, and pretend the sphere is a large planet such as the Earth. We know the gravitational field strength near Earth's surface is 9.8 newtons per kilogram. We've seen that in experiments and also in many calculations that we've done. But we haven't discussed what the field strength at other locations would be yet. So looking at the diagrams, which one do you think best represents the gravitational field around a sphere of mass such as the Earth, and why? Well, there are subtle differences between the pictures. In one case, the largest arrows are farther away from the sphere. In another case, the arrows have all the same length, so distance from the sphere doesn't affect the strength of the gravitational force or field. And in another picture, the largest vectors are closer to the sphere and the smaller vectors are farther away from the sphere. So Newton was one physicist who considered this question, and he came up with an answer for it. Which one do you think he said was correct? A, B, or C? Well, Newton selected C as the correct choice, and he even came up with a law of gravity which describes how gravitational forces would change based on the distance between the mass and the sphere that's attracting it. Newton said the farther away you get from the sphere's center, the smaller the gravitational field or force would be. Pictured here is Newton's law of universal gravitation. M1 and M2 are different point masses that are separated by a distance r. In this formula, any sphere of mass can be treated as a point mass, as if all the mass in the object was concentrated in its center. Big G is the gravitational constant, which has the value 6.67 times 10 to the minus 11. And the units are Newton meters squared per kilogram squared. We'll see why those are the units here when we do a calculation shortly. Now, by Newton's third law, the gravitational force of M1 on M2 has the same magnitude as the gravitational force of M2 on M1. Therefore, we only really need one formula to calculate the strength of the force between these particles. One common mass that we use all the time is the mass of Earth, 5.97 times 10 to the 24 kilograms. It's a big mass. And we also often use the radius of Earth for objects that are on Earth's surface, and that's 6.37 times 10 to the 6 meters. A little over 6,000 kilometers. Now there's a subtle difference between a force and a field. And we've actually been using a field strength all along in our calculations. The gravitational field strength at any particular distance r from the center of a mass m1 is the force that would be applied per kilogram if any mass were present at that distance. And the only difference between the formulas here is that when we're calculating the force, we know what M2 is. We can actually plug it in. If we're calculating the field strength, though, then we don't know what M2 is, so we leave it off. And as we'll see in our calculations, the units of force will come out to newtons. But the units of field strength will be newtons per kilogram. Subtle difference between these formulas.